Dear students, in our previous class, we discussed about what are filters, different types of filters, and some basic definitions related to filters like pass band, stop band, cutoff frequency, etc. So today, we will discuss about types of filters. First type of filter is a low pass filter. See, low pass filter means a low pass filter is a filter that passes signals with a frequency lower than a certain cutoff frequency and attenuates signals with frequencies higher than the cutoff frequencies. So you can see a graph plotted voltage against frequency. We can plot a graph gain versus frequency also. So in this graph, V0 is a output voltage, F is a frequency. V maximum is a maximum voltage, maximum output voltage. So in this graph you can see pass band and stop band. See where here FC is the cutoff frequency. In this filter, it allows the low pass filter allows only the signals below FC. They are called pass band, and it attenuates, it cut off the signals above FC. That is called stop band. See, in low pass filters, there are two types of filters you can see. One is RC low pass filter. RC means the combination of resistance and capacitance. And other low pass filter is RL low pass filter. It is the combination of resistance, inductance, low pass filter. First we will discuss about the first low pass filter, that is RC low pass filter. You can see the circuit drawn for RC low pass filter. So there is a resistance and capacitor. Both are connected in series. VI is the input voltage and V0 is the output voltage. So to give the signals to the input, and they have to measure the V0 at the output across the C. See, a simple passive low pass filter that can be constructed using a series RC circuit. The input signal VIN is applied to the series combination of a resistance R and a capacitance C. The output V0 is taken across the capacitor. Here, the reactance of a capacitor, that is nothing but the XC. Okay. XC is the capacitive reactance or reactance of a capacitor. XC equal to 1 by omega C. That is equal to 1 by 2 pi f C. The reactance of a capacitor varies inversely with the frequency because X equal to 1 by 2 pi f C. Therefore, Xc is inversely proportional to F. The reactance of a capacitor varies inversely with frequency while the resistance remains constant. At low frequencies, the capacitive reactance Xc will be very large compared to the resistance R. Hence, the capacitor acts as an open terminal. The output voltage measured is numerically equal to the input voltage. As the frequency increases, the value of Xc decreases because Xc and F both are inversely proportional. Therefore, as the frequency increases, the value of Xc decreases. and hence the output voltage also decreases. At very high frequencies, the value of Xc is very small, such that the capacitor acts as a shorted terminal, and hence the output voltage will be 0. Here, suppose I is the current flowing through the circuit, through the RC low pass filter circuit, then so according to Ohm's law, current equal to voltage by resistance. Here I is equal to VIN by Z, where Z is the impedance of the circuit. This Z is depending on the resistance and Xc, that is the resistance and resistance of the capacitor Xc, that is called capacitive reactance. Therefore, you can see the equation 1. So current I equal to VIN by Z, where Z is square root of R square plus Xc square. Then the output voltage across the capacitor. See, suppose I is the current flowing through the circuit, which is flowing through resistance and also through the capacitor. So V0 equal to I into Xc. Voltage across the capacitor is V0. So I is the current flowing through the capacitor. Therefore, V0 equal to I into Xc. That is the voltage across the capacitor. But from equation 1, I means VIN by root of R square plus Xc square. Therefore, so V0 is equal to VIN divided by square root of R square plus Xc square into Xc. Therefore, if you simplify that equation, then so you will get the equation 2, that is V0 is equal to VIN divided by square root of 1 plus R square by Xc square. But here the denominator term R square plus Xc square. See, we know that Xc is equal to 1 by 2 pi Fc. Therefore, R square by Xc square equal to 4 pi square F square R square C square. So that is proper. Here frequency is proportional to the F. So R square by Xc square proportional to F square. The rest of the terms 4 pi square R square C squares are constant. Therefore, R square by Xc square proportional to F square. So in this case, so we will discuss different cases, that is when F is small, F is large, and if X equal to R. First, suppose the frequency of the applied signals is small, then R square by Xc square is also small, because F is inversely proportional to Xc. Therefore, if F is small, R square by Xc square is also a small. Then equation 2 becomes, in equation 2, suppose when denominator term is small, V0 is large. Therefore, low frequency signals are transmitted. Suppose F is large, then R square by Xc square is also a large, because R square by Xc square proportional to F square. Therefore, if F is large, R square by Xc square is also a large. Then V0 is small from the equation 2. Therefore, high frequency signals are attenuated or cut off. So in third case, suppose capacitive reactance equal to resistance of the circuit, resistance X equal to R. Then in equation 2, if we substitute V0 equal to VIN divided by square root of 1 plus R square by R square, because X equal to R. So that is equal to VIN by root 2. So 1 by root 2 is 0.707 Vi or 70.7% of Vi. Output voltage is equal to 70.7% of the Vi. That is frequency at which the gain or output voltage decreases to 1 by root 2 times its maximum value. That is called cutoff frequency, denoted by Fc. Okay. So here we can define the Fc from the graph corresponding to V0 by root 2. So the frequency is Fc. Therefore, the cutoff frequency is defined as the frequency at which the gain decreases to 1 by root 2 times its maximum value is called cutoff frequency, denoted by Fc. So this is the condition for the cutoff frequency. Therefore, at Xc equal to R, F equal to Fc. From the graph also you can see that if X equal to R, F equal to Fc. Xc means 1 by 2F into C. Here C is missing. So Xc equal to 1 divided by 2 pi Fc into C, that is equal to R. Therefore Fc, if you cross multiply, Fc is equal to 1 by 2 pi Rs. So this is the expression for the cutoff frequency. The capacitor offers low reactance for higher frequencies and high reactance for lower frequencies. Hence, the band of frequencies varying from 0 to cutoff frequency Fc are passed through the resistance R to the output, and the rest being directed out of the circuit through C. The working of RC low pass filter can also be explained as the capacitor offers low reactance for high frequencies and high reactance for low frequencies. Hence, the band of frequencies varying from 0 to Fc are passed through R to the output, and the rest being directed out of the circuit through C. The second low pass filter, the second one is RL low pass filter. See the circuit diagram for the RL low pass filter is shown. Inductor and resistor are connecting in series. Inductor is connected to the input terminal. So output we have to measure across the resistor R. A series RL network can be used as a low pass filter by taking the output voltage across the resistor. Here I is the current flowing through the circuit. Then I is equal to VIN by Z, or VIN by root R square plus XL square. XL is the, for capacitors, XC is the capacitive reactance. Similarly, like for inductors, XL is the inductive reactance. XL equal to omega L equal to 2 pi FL. Therefore, XL is directly proportional to frequency. XL equal to 2 pi FL. But in case of, as in the case of capacitor, XC equal to 1 by 2 pi FC. An AC input signal, we can explain the RL low pass filter like this. an AC input signal is applied across the series combination of inductance L and resistance R, and the output is taken across the resistance. The reactance of an inductor varies directly with frequency, but the value of resistance is constant. At low frequencies, the inductive reactance XL will be low compared to the resistance R. Hence, the inductor acts as a shorted terminal. At this state, the output voltage measured V0 measured will be nearly equal to the input voltage VIL, as the maximum voltage is dropped across the resistance only. As the frequency is increased, the value of XL also increases, because XL equal to 2 pi FL. XL equal to omega L equal to 2 pi FL. Therefore, as the frequency is increased, the value of XL also increases, and hence the output voltage decreases. At very high frequencies, the value of XL is so large that the inductor acts as a open terminal. Hence, no voltage is dropped across the resistor, and hence the output voltage measured will be 0. See, in equation 1, I is equal to Vin by root of R square plus XL square. The output voltage across the resistor is, suppose V0 is here, V0 in the circuit, V0 is the output voltage across the resistor R. So then according to Ohm's law, V equal to IR. So V0 equal to I into R, where I is the current flowing through the circuit, through the inductor and resistor, L and R. So V0 equal to IR. From the equation 1, I is equal to, substitute the value of I from the equation 1. Then you will get equation 2. By simplifying, you get the equation number 2. But we know that XL square by R square. See, XL is the 2 pi FL. Therefore, XL square by R square equal to 4 pi square F square L square by R square. So, 4 pi square L square by R square is a constant. They are the constant terms. Therefore, XL square by R square proportional to F square. Here we can study the different cases. If when the frequency of the applied signal is small, when the frequency is large, okay, and if XL equal to R. Similarly, like previous RC low pass filter, here also we can discuss the 3 different cases. First case is for lower frequencies. When frequency is small, XL square by R square is also a small, because XL square by R square proportional to F square. Therefore, if F is small, XL square by R square is also small. Then V0 is large. That is, from the equation 2, okay, from the equation 2, V0 is large for small values of XL square by R square. Second case, if F is large, that is for the higher frequencies, so XL square by R square is also large. Then from equation 2, V0 is small. Hence, the circuit allows low frequency signals and attenuates high frequency signals. Suppose the inductive reactance equal to R, XL equal to R, Then if you substitute XL equal to R in equation 2, you get V naught equal to Vin by square root of 1 plus XL square by XL square, that is equal to Vin by root 2. So this is the condition for the cutoff frequency. Therefore, cutoff frequency can be defined as the frequency at which the gain or output voltage becomes 1 by root 2 times the maximum gain or maximum voltage is called the cutoff frequency, Fc. Therefore, at XL equal to R, you know that F equal to Fc. Therefore, XL means 2 pi FCL, that is equal to R. Therefore, Fc, the expression for the cutoff frequency is R divided by 2 pi L. It is depending on the resistance and inductor. So, this is the expression for the cutoff frequency for LR low pass filter. In next class, we will discuss about high pass filters. In high pass filters also, we have to discuss two different types: RC high pass filter and RL high pass filter. Okay. Thank you.